And so he wants to nuke another country, and what is the launch code? Nuclear launch code. And he asks the vice president. The VP sends a launch code 9/11. Now the messages, the interaction that they have, it's taking place between these two people is encrypted, right? But how does this encryption exactly work? So say you send a message to your best friend, and then the letters of this message, the numbers or whatever, they're encrypted in some numbers, and that decryption code is there in the receiver's device, and they can decrypt it and read whatever you have sent. Now there's a guy, Vladimir, name inspired from Hollywood. He wants to hack this and get the code. Okay, so he needs to decrypt that message. Now, one of the very fun, useful things that we use in our daily encryption process, the messages that we send to each other, that process is called RSA encryption process. Or I guess there are people in number theory and cryptography here, they can talk about it much better than me. And one of the fundamental things concepts that we use in this RSA algorithms is the factoring, finding out the prime factors of a very large number. So the encryption is done using that. So Vladimir has to find out prime factors of a very large number. That's how he can hack the messages. Now let me show you something. Don't get worried about the code. It's a very simple code. You can get it online. It's to find out the prime factors of a number. Just look at the arrow parts. Even after 1 minute 16 seconds, the computing power has not been able to find out the prime factors of a very large number I put in. So how did I get the large number? I just took some very large 15 digits prime numbers from Wikipedia, and okay, so prime numbers from Wikipedia, multiplied by a very large number with very large prime factors. And see, even after 1 minute 16 seconds, it has failed to find out even one factor of that large number. So these sorts of problems that we encounter, that these problems are very hard for our classical computers, our classical computing power to solve. It's a sort of called hard problems. I won't go into the details, but okay, they're hard problems. Exactly, hard problem. It takes a lot of time. So it depends on the computing power. So I'm just doing it in global collab, and if I got build a bigger computer, better computing power, probably I would have been able to find out the prime factors. So it depends on the computing power. And say a hacker has a very high computing power. Okay, so he or she can decrypt those encrypted codes and find out prime factors. That's another problem. The everyday messages that you send, you can go through and see the encryption code. You can see very large number, like hundreds of digits in that encryption. So as you can understand, for any sensible hacker won't spend that much of money to just decrypt your messages. But when the computing power increases, ease of hacking also increases. So in this classical computing setup, we essentially have two problems. Finding the prime factors of a very large number, and two, this is not a foolproof encryption system. First one, I just showed it to you, and the second one, well, if the computing power increases, it is theoretically not impossible to crack the encryption. Anyways, and this is where something, a magic wand physicists developed in the 20th century, quantum mechanics, comes to rescue. Quantum mechanics, based on quantum mechanics, quantum computing is being developed. That can solve both of these problems. There's something called a Shor's code that can find out the prime factors of a number, even though till now the practical application only has been to number 15. But okay, theoretically it's possible, and theoretically it can provide with a foolproof encryption system. Let's go to a much more mundane somebody asks you what's the color of the sky, you say blue. Why? Well, it's blue. So here we need to find out the color of the sky. The basis of this again lies in quantum mechanics. This is something out because of Rayleigh scattering. And to explain that with Rayleigh scattering, one of the very basic things you have to understand is what light is made up of. And thanks to Max Planck, he just gave a formula that somehow described the Blackbird radiation curve. But anyways, the light is made up of some packets of energy. Okay, here you can see dollar, but I find money nice. But okay, so some packets of energy. And these tiny packets, each of these tiny packets is called a quantum. Now I guess you have the idea where the word quantum in quantum mechanics comes from, because on the basis of this, all the formulations of quantum mechanics were done. So let's have a yeah, there was some history of download, but okay, figures are absolutely sure. I don't know why my laptop is getting very slow. Yeah, okay. So welcome to my talk, what the heck is quantum mechanics? There was supposed to be a drum roll, but okay. It's fine. What's your favorite field in physics? Okay, how many for astro? Only this many. That's it. Okay. I thought the percentage would be bigger, but okay, whatever. Well, this 99% is not on the basis of any statistical data. It's just whatever. Okay. Astrophysics is amazing. Obviously, you do a lot of maths, and you can find out the intricacies of this beautiful majestic galaxy and the universe. It's beautiful. Astrophysics is amazing. Whereas, you do maths, you do more maths. But what can you see? What majestic world can you see? Essentially, nothing. And even I have represented nothing here with a black screen. But even that's something you can observe. You can see a black screen. In the quantum world, it is beyond our imaginative power. It is beyond our intuitive power. So you just do maths. Maybe the maximum you can get is you can get some value, like you can predict some experimental results. That's it. You won't be able to see such nice, amazing pictures. And this is, in my opinion, is the beauty of quantum mechanics. It gives you a way, a path, to peek into some world that is unimaginable to us. Some world that we cannot send a very tiny microscope comparable to JWST, like equivalent to JWST. And that will take some amazing photos of atoms, molecules, and whatever. No, we can't do that. So, and also, this is also true that nowadays, every branch of physics, even most of the branches in chemistry and biology requires even JWST to take those photos, they need a spectroscopy, and spectroscopy is based on quantum mechanics. So even if you're an astro enthusiast, you need to know quantum mechanics. Quantum mechanics is something, it's a tool that we have, not a tool, but a development that is essentially applicable to any field, in almost any field. Okay? Let's just quickly glance through the prerequisites to study quantum mechanics. What are the prerequisites? In maths, you need to know complex numbers, you need to know calculus, you need to know linear algebra. And linear algebra. That's the most important thing that you need to understand, not only understand, but assimilate, to understand all the concepts, to understand the visual interpretations of those concepts, to understand quantum mechanics. Why? You see, when quantum mechanics was developed, there were only some experimental results and it was not fitting to any existing theory. So the physicists and mathematicians, they had to incorporate it into some existing mathematical structure. And that structure was linear algebra. So you need to understand linear algebra, you need to understand the visual representations, you need to assimilate linear algebra. That's maths. In physics, well, hopefully I got you there. Considering you know most of class 2 physics. So I hope you know most of class 2 physics. In that case, you can just go and start learning quantum mechanics. You don't really need anything from the college level. Let's start about quantum mechanics. Schrödinger's cat, I guess you all know Schrödinger's cat. Can somebody just tell us? What's Schrödinger's cat? Somebody. Yes, preferably for MS-23. Somebody. Yeah.
So it's basically it's a mechanism to explain quantum. Actually, Schrödinger invented this sort of experiment to show the ridiculousness of quantum mechanics. But basically, there is a radioactive atom that has a 50% chance of decay. If it decays, a detector detects it, and that triggers into a breaking of a poison pipe, which can kill the cat. Since there is a 50% chance of the atom decaying and not decaying, it exists in superposition of states. And since the state of the cat is also entangled with the state of the radioactive atom, the cat is also in a state of alive and decay. But that is against a common equation that it cannot be, because it's classical. It should be ruled by classical.
It's in a well, you're right. You're absolutely right. But it's in a superposition state of dead and alive until we observe it.
Yes.
That's a very important point. Until we observe it. That's essentially Schrödinger's cat. Does anyone have any questions for Schrödinger's cat? Because I don't want to make my lecture long by just talking about Schrödinger's cat. Maybe it's fine. Okay. I myself have formulated another thought experiment. Stay tuned for it. So yeah, as I told you, quantum mechanics was a shot in the dark. Nobody knew anything about what is it. It says we have some experimental evidence. Let's try to give a theoretical framework to it. And hence, what they needed were some postulates. That's it, postulates. Why postulates? Because see, you have some evidence. You want to build a theoretical framework, but you need something that you want to believe in. So, okay, this is correct. And then you can build a framework. And if the framework doesn't give proper predictions, then that's wrong. The postulates are wrong. But you cannot question a postulate because it's postulate. So yeah, there were some postulates were given to interpret quantum mechanics, and that was Copenhagen interpretation. There's another interpretation, Annwoy's interpretation. But I'm not going to it much later. Copenhagen interpretation was the first interpretation of quantum mechanics that was given. I think you have seen this photo, this famous photo of all the legendary physicists coming together. So I'll go into the postulates because see, that's the essence of quantum mechanics. But I will not delve into the rigorous mathematics behind those postulates. Postulate 1. So you have a personal space, right? You do not want anyone to interfere in that personal space. You can say that is your space, that is something that you have, it's your circle, it's your sphere, right? So a system, a physical system, isolated. Because see, if she now puts her hand on your shoulder, well, that's a violation of your space. But it's a violation. If it's wrong or right, we will not go into that, but it's a violation. Okay. So I am just keeping you isolated from it. So any physical system, an isolated physical system, has such a personal space. How do we mathematically formulate that personal space? That is something we need a linear algebra for that. So the personal space of an isolated physical system is a 2D complex vector space. Even though I showed you a two-dimensional real space, x-axis, y-axis, well, it's not really it, okay? Because a complex vector space, you can create a vector space with anything you want. You can create it with hippopotamus, you can create it with this adapter, you can create it with Mike or whatever. Okay, you can create it with anything. But it has to follow 8 actions. There are 8 rules that anything has to follow to become a vector space. You can go to Google and search it. But okay, so complex numbers follows those rules. So complex numbers create a vector space. Complex vector space make the problem much easier because what's a 2D complex vector space in real space? Can anyone tell me what's the dimensions in real space? If I
What was the question again?
So if I have a complex vector space that's 2-dimensional, if I change it to a real space, how many dimensions will there be?
Divided by 2.
Okay.
Wait.
I have a complex vector space that's 2-dimensional, right? 2 axes, 2-dimensional. And there's another, I actually now change it to real space. So in that real space, how many dimensions will there be?
4.
Yes, 4. So as you can see, 4-dimensional real space is very hard to visualize and draw it. And there are other advantages of taking a complex vector space. So this is just vector space, and this is called a Hilbert space. This Hilbert space, there are essentially 2 properties of Hilbert space. There's Cauchy complete, and the second is equipped with inner product. There's a boundary that you can see, right? That means box. Now what does this box represent? It represents Cauchy completeness. Like what I wanted to tell about Cauchy completeness. Do you guys know about Taylor's expansion, right? Taylor series, Taylor's expansion. Well, if you take e to the power x, you can expand it in terms of x squared, x cubed, and such. There will be an infinite terms. You take the summation of those infinite terms, you will get e to the power x. Now see, this x squared, x cubed, in which vector space do they lie in? Polynomial vector space. Because they also follow those 8 rules. So they also form a vector space. And they are here, in place of I cap, j cap, k cap, we have x to the power 0, x to the power 1, x squared, x cubed, and such. These are the basis vectors. Okay? So now you're taking some combination of vectors from the polynomial vector space, taking their sum, is going out of polynomial vector space and becoming an exponential function. Right? You're taking the sum, you're taking some elements from that polynomial vector space and taking a sum of that is going out of the polynomial vector space because it's giving e to the power x. It's just a Taylor series expansion of e to the power x. Summation of polynomials going out of polynomial vector space, going to exponential. So this cannot happen in quantum mechanics. As you can clearly see, you have a space associated with a particle, some quantum particle, and you take the summations of vectors from that space, and it goes out of the vector space, so it's not associated with the particle anymore. That's like clearly absurd. So yeah, it has to be Cauchy complete. That means any summation of any sort of vectors, infinite summations, they have to stay within that boundary of the vector space. And the second thing is equipped with inner product. I am again not going to go into the details of inner product, but inner product essentially you can visualize it as dot product. It's very close to a dot product. That's it. Just take 2 vectors A, B, and it's a projection dot product. So these are the characteristics of Hilbert space and the state of the system. So we got the vector space associated with the system. With the system. But see, now she is writing something on a notebook, right? So just before this, you were listening and looking at me. Just before this, maybe you were outside the room. So there is a space associated with you, but you have a particular state. So we can define all these as different states, right? So every such isolated physical system has states. And that state, how do we represent that state? It's by a vector. Just a vector, but not our general everyday vectors. We don't draw an arrow above the vector. We just represent it by something like this, as you can see. It's called a ket. Okay. Again, it's just a vector, but in a complex vector space. That's it. Don't get frightened by it. It's very simple. But I have to make a special mention here. So whenever we talk about quantum mechanics, who comes to your mind? Which physicist or convention? Feynman, okay? Yeah. Damn, okay. Anybody else? Who comes to your mind? Schrödinger. Einstein. Only one person said Dirac. But it is essentially Dirac who made the formulation of quantum mechanics possible. Because all this that you can see is a ket, and if you take the dual space of a ket, that's become a bra, and that this bra and ket, they form the bracket formulation. It's called the Dirac formulation. Dirac formulated the foundation of quantum mechanics. So without Paul Dirac, no quantum mechanics. Thanks to him, special mention. Postulate 2. You have an extensible string, right? You can just think of it, right? Anyone who has an extensible string, or you can imagine it, right? Okay, an extensible string. And you can do 3 operations on that string. You can move it in space. You can rotate it like this, and the rotation won't really extend it or compress it. Just normal rotation. Or you can extend or compress it. Extend, compress, I did put it in a different way, but extend it or compress it. Now see, in movement or rotation, the length of the string is not changing at all. It's just staying constant. But when you're extending it or compressing it, the length will change. So movement and rotation, these are called unitary transformations. They are sort of unitary transformations because they are preserving the length, and that preservation of length, so the transformation. What's a transformation? I just showed you the visual representation. That's also a transformation. But you can use matrices to also like to show a mathematical transformation. So unitary transformations, they preserve the length of the vector. You can take any vector, you can move it in space, you can rotate it, the length of the vector won't change. That's unitary transformation. Now, it's also written there that preserves length, so preserves probability. In QM, the length of a stent vector will, it is related to the total probability of finding that system. Okay, you can find the system in different states or different projections of the vector, x projection, y projection. But you will find the system, right? It's there. If you make an observation, you will find the system, right? So the probability, total probability of finding the system has to be equal to 1. And that is essentially what we call normalization. So we make sure that the total probability of finding a system is always 1. And now I guess you can see if you change the length, the probability, total probability will change. So the transformations for isolated quantum systems, closer isolated quantum systems, the evolution of them in time. So they can, this tree is walking here right now, but this length is not changing. So it's walking as a unitary transformation, right? So in time he's evolving, his position is evolving, his state is evolving, but his length is not changing. So this is unitary transformations, and this is exactly what the second postulate states, that every quantum system can only go through unitary transformations in time. No other sort of evolution can happen for any closed quantum system. Postulate 3. Why did I write not really? Because to understand postulate 3 properly, every bit of it, you need to learn certain things before, a lot of mathematics. So, and it's measured, it talks about measurement. Just think, when you're doing a measurement, is a system staying isolated anymore? You're making a measurement. Is the system staying isolated? It's not. You are disturbing the system. You're somehow disturbing the system. So this is something measurement that physicists and scientists couldn't wrap their heads around for a very long time. It comes to the world. It's very simple. You just go, see the chair is here. Oh, nice. It's a nice, simple observation. But in quantum mechanics, the observation does not happen like it. Because how am I observing the chair? There's a light, right? That's coming to it. It's getting reflected and coming to my eyes. So I'm observing the chair. But that light has some energy. And that energy is not disturbing the chair. But when I'm going to say a quantum world, such tiny particles or whatever, the light or any other mean of observation that you're going to use is going to disturb the system. And when you disturb the system, the state of the system will change in a predictable way. In some cases, a predictable way, but it will change. So that is the problem of measurement in the quantum world. You cannot ever observe the state vector or the state of a particle itself. You will observe any one of the orthogonal components. What's orthogonal? So like two components are 90 degrees, that's called orthogonal components. Okay. So any of the orthogonal components associated with some value, what we call an eigenvalue. I'm not going to go into the details of eigenvalue. You have to see linear algebra and to find it out. But okay, so that value is called the observable. That's what you're going to observe. And associated with one of the components or one of the orthogonal components. You can dissociate a vector set between the different orthogonal components. It will depend on the case which orthogonal components you want, but only one you can get at one point of time. So the system will collapse. So it's like, yeah, so she is now in a very nice mood. She puts her hand on her shoulder and she kind of collapses. She is angry right now. It's sort of a collapse of one state. Okay, so her mind might be now in different states, but when she puts her hand, she is angry. So that's one state. So yeah, it's a collapse. It's sort of a collapse that happens. It's not sort, it's a collapse that happens when you make a measurement in quantum mechanics. I just make one slide for postulate 3 because I don't want to go into the details of measurement. Measurement is something very complex, but you should feel encouraged to read about it. Postulate 4. It's something it's a postulate that I find the most easiest, or find the easiest if I understand postulate 1. So you have personal space of one human being, you have personal space of another human being. Now those they become very good friends, close friends, right? And then their personal spaces are sort of voided by the other person, and they create a new next friend space. That's a new space, friend space, right? And similar scenario takes place when two isolated physical systems are taken together. We call it composite systems, but it's sort of it takes together, and that together have a new higher dimension level space. So I told you right now, one quantum system will have a two-dimensional level space. So if you take now two isolated quantum systems, they will have a new higher dimensional, actually four-dimensional level space. Okay, if you take two systems from and how do we get this new space? We get it by tensor law. Just a minute, that's it, nothing else. That's the essence of quantum mechanics. Quantum mechanics only consists of these four postulates. These are the basis of quantum mechanics. If you understand this very clearly, and I can assure you, it is not easy. It takes time, it takes a lot of thinking, it takes a lot of practice, reading to understand four postulates properly, to assimilate the idea of it. But on the rest, everything else is just built up on these four postulates. That's it. This is the essence of quantum mechanics. Well, my talk is not yet finished. So we'll go into some fun stuff. Heisenberg's principle. Anyone? What do we mean by Heisenberg's? Anyone other than you? Anyway, come on. Hey, you studied this in class. We all studied this in class 12, but in a wrong way. Anyways, so chemistry also. Yeah, it doesn't matter. Class 2, whatever. So somebody, come on. Yeah.
If we know the position, we can't know the momentum, and if we know the momentum, we can't know the position of the particle.
Any modification on that? Yeah, very close. Any modification on that? Somebody, come on. Okay, you. Okay,
microscopic particle. It is valid only for a microscopic particle.
Yeah. And what did she say? She said, if you know the position, you cannot know the momentum. If you know the momentum, you cannot know the position. Is it completely right? Yeah, and anything else? Anything else you want to add?
We cannot know the position and momentum of a state with perfect precision at the same time.
Yes. So that's what we study about as a uncertainty principle. You can see the equation del x by del b is greater than equal to h by 4 pi. This del, we call it uncertainty. You know, in terms of statistics, it's the standard deviation. That's it. It's the standard deviation. You can find a general uncertainty principle. So Heisenberg's uncertainty principle is just a special case. When you take positional momentum, you can take any observable, you can observe a lot of other things than positional momentum. And you can just Google it, it's very simple, basic maths, nothing difficult. You can find the proof of general uncertainty. That will give you, like, if you take two observables, take the standard deviations of them, and that will be greater than equal to some number. That's it. But there are other interpretations of uncertainty principle. The one you told is what we all read. But nowadays, this is coming up with a much, mathematically, not politically, mathematically correct way of interpreting this equation. That is, we make a lot of measurements on a quantum system and find out the position and momentum. The standard deviations of them, the multiplication of the standard deviations will be greater than equal to this number. That's it. No, like, if we know the position with such certainty, we cannot know momentum with such certainty. Those are sort of our classical ways of trying to understand the quantum world, but our classical intuitions do not work in that way. So I'm not saying that is wrong, but this is a much more mathematically correct interpretation. You just take the standard deviations. That's what the mathematics gives you. Okay. So in quantum mechanics, it's good to stick with mathematics, though I have not to do. Next, entanglement. Something like a very fancy word, right? Now, Hollywood uses this a lot. Marvel comics. Yeah. So I have two boxes of flowers. One box has a white flower and a blue flower. The other box has a green flower and a yellow flower. Okay. Now I give it to. I can just pick one box, take out the flowers, and send it to you too. Okay. Send it to you. You guys knew that with white there was blue, with green there was yellow, right? So if you get white, you immediately know that your friend got blue. Even if you are at Arctic and your friend is in Antarctica, you know that if you got white, your friend got blue. If you got green, your friend got blue. You know it, right? Okay? These are the only two possible pieces. So just by looking at the color of your flower, you get to know what color flower your friend got. So it's like your flower and your friend's flower is a sort of interconnected or entangled, as physicists like to say. You may ask me that, well, on the basis of entanglement, there has been so much of work, especially quantum information and quantum computing is essentially based on the idea of entanglement. And that is right now one of the most promising fields in physics. So is entanglement really so simple? I mean, yes or no? Because if you want to understand entanglement in a much rigorous way, again, you need to go to the mathematics. And you know what will happen here. So for postulate 3, you saw when we are doing the measurement, postulate 1 and 2, they are not working anymore because we are not keeping it closed to the system. And here comes your postulate 4. And you have, so in place of flowers, you can take quantum states and you can, the entanglement will sort of mean taking the tensor products of those, of the vector, of the Hilbert spaces of those two quantum systems. Yeah. So that's essentially the essence of entanglement. EPR paradox does an impact. Two of the most important works in the history of quantum mechanics, in the history of physics. I don't have the time to go into the details of EPR paradox and balancing inequality. If anybody knows about EPR paradox, can you shed some light on it? Anything? Yeah, Anand, you are now. Okay, now demonstrate this.
Locality basically means
not locality, EPR paradox.
I think it's Einstein and other scientists they try to disprove the postulates of quantum mechanics. Basically, they assume that the reason, for example, sometimes we get an unexpected outcome in quantum mechanics. It's not because it is purely probabilistic, but there might be some hidden variables that are mentioned there. And the second is that if we make any change at a certain point, it will only change neighboring points. It will not change a point that is a lot of distance.
That's one of the most important things in nuclear paradox. So it's Einstein-Podolsky-Rosen paradox. It was, Einstein did not like quantum mechanics. Not only Einstein, many people who developed quantum mechanics, they hated it. And Einstein started researching on metaphysics to disprove quantum mechanics. So he went to such a level. Anyway, so quantum mechanics really did trigger them a lot. So EPR paradox was, in a sense, to invalidate quantum mechanics. And the most important thing is, EPR paradox is considered as one of the most intellectually vibrant papers in the history of physics. It was such an amazing way of trying to disprove a theory. So I would suggest you to go and read the paper, or there are multiple explanations. So go and read about it. But yeah, the essence of EPR paradox is that the quantum mechanics were in essence violating two very major assumptions we make in physics: locality and realism. What is locality? Locality says nothing. Just if I take this chalk here, that's not going to affect Aman sitting there. And if my words still affect him, but if I pick up the chalk, it's not going to affect him. So my action here is not really affecting something at a very far distance. Okay. So anything essentially cannot travel faster than light. That's very relativity. But quantum mechanics was in a way suggesting that information can travel faster than light. Spoiler alert, you cannot use it for signaling. There's something called the signaling theorem. Yes, information travels faster than light, but there's no way you can use it for your own purpose to send some information faster than light, where instantaneously. That's not really possible. But okay, yeah, information does travel faster than light. Okay, so locality was first assumption. And the second assumption is realism. Again, I'll go to the color of the chair. The color of the chair is yellow. You just go observing, you see it's yellow, you get to know it's yellow. The color yellow was already there, right? So this is realism. By observation, we just find out something that was intrinsic to the system, that was already there. These two observations, these two assumptions we make in physics. So Einstein said the postulates of quantum mechanics, theory of quantum mechanics, is violating these two assumptions. These very important assumptions which are considered correct, which were considered correct. Unfortunately, in his time, Schrödinger said that St. Andrew and whatever Schrödinger didn't really give any proper, nice answer. It took almost 25 or 35 years, I guess, to come to John Bell to his work. Yeah, 25 years, right? 25 or 35 years. Einstein was not really alive to see an answer to one of the greatest questions posed in the history of physics. So yeah, John Bell did some mathematics and thought experiment. You can go to your room, Google CHSH game. That's it, CHSH game. It was not used by Bell, but it was used by 4 physicists. One of them got Nobel last year one of them got Nobel. So yeah, John Bell showed in classical cases when you're making this playing this. I'm talking in terms of CHSH game, say. So when Bell did it in terms of CHSH game, when you're playing this, there's a term Q. Okay, some term Q. If you play it in a classical way, that term Q will always be more of that will be less than 2, less than equal to 2. But if you take a quantum strategy to play the game, that term will be less than equal to 2 root 2. So the quantum mechanics is sort of changing the term, and that is essentially changing the winning probability of one of the players in that game. So quantum strategy. And if the only two assumptions that were took in the classical case was locality and realism, but quantum mechanics was showing a different result. So yeah, quantum mechanics has to be either non-realistic or non-local or non-local and non-realistic, both. It's a matter of research what it is, or if Bell was wrong, but till now no, Bell was not wrong. Bell was actually correct, and that Bell laid the foundation of quantum information and quantum computing, using entanglement for an absolutely new world. Yeah, so I would really advise you to go to your room, read about peer paradox, read about Bell's inequality, read about CHSH. So thank you for waiting for such a long time. This is my topic. So yeah, you have a box. Okay. In that box, there's a coordinate system, x-axis and y-axis, and this is R, it's blue R. Okay. Now, an ideal chameleon is placed inside the box. What's an ideal chameleon? You cannot ever observe it. It always matches with the color that's on here, that's it on board, or whatever the color that falls on it, whatever. You cannot observe it, and it's a very tiny chameleon. So compared to this very tiny, so you take your 1 point on this surface, something like this. And the box is kept closed. The chameleon can only move around this path. That's the only path it has. And the box is kept closed. Okay. The chameleon is moving inside the box. Whenever we are opening the box, the chameleon stops moving. And see, there are two light sources here. There are two light sources at the top and at the right side. So one of the light sources will turn on at random. One of the light sources will turn on, and when you observe, you can see the shadow of the chameleon on either y-axis or x-axis. So you get to know the position of the chameleon only along one axis, not along the both. And after the box is getting closed, the chameleon is still frightened, so it won't move for some time. So if you add in that period of time, if you open the box again, only the same light will turn, so you will observe the thing. This is my thought experiment. I thought that I would talk about the points on the basis I made it, but well, I want your opinion. Tell me whether you think it's better to understand the quantum world as well, because this is again a classical way of interpreting quantum world. It has limitations, but is it better or not? Tell me your opinion. Yeah.
It is better. Okay.
Okay, why?
That's because when you're dealing with wave function collapsation and dynamics, there is one idea that if you're trying to find the expectation value of some observable, which is basically essentially the average, but you can't just take a system and keep measuring its wave function repeatedly for the average. Why? Because when the wave function is measured, it collapses to something called a line dependent function, which is localized at point.
Yeah.
Since the wave function is time dependent, after making a measurement, it takes some time for the line dependent. You can say reset back to the original wave function. So within this time, you have a higher probability of getting the same measurement if you take a measurement again. That's why typically what scientists like to do is, prepare an ensemble of system, prepare an ensemble of, let's say, 100 of the same states, and get a measurement of each state to get an empirical value of the average effect. So this experiment demonstrates that because of the scared chameleon, it cannot move for a while, which is basically sort of an analogy to the wave function recollapsing to the same value if you take a successive value. So
yeah, that's thank you for that. That's one of the points I kept in mind by making this whole experiment. Another point is the measurement I talked about. It was not just general measurement. General measurement we need in quantum computing because quantum computing requires a very high precision in measurement and control in measurement. So that's why we require general measurement. Most of the measurements in the quantum world can be done using projective measurement. So as the term says, it's sort of a projection. It's not solid, it's a projection, but in a complex way. So you can see here, you're observing the projection of the position of the chameleon. Why the projection? So I also get the projective measurement in mind. And thank you. Projective measurement in mind. And yeah, another point is, see, shredding this cat, you know that the cat is there and the cat is either alive or not alive. But to be frank, in a quantum world, we don't really know what exactly is the situation until we're observing. And then we don't know what's exactly the situation. Some collapse situation we get to. But till then we have no idea what's happening in the quantum world. So here, if we close the box, we have no idea at which point the chameleon is. So these are some basic things that you have to keep in mind while devising this experiment. But thank you. And this is on side. What is quantum physics? If you take quantum mechanics, there's a population. That's how particles in the quantum world or systems in the quantum world, they move, they move and their trajectories and everything, the energy and everything are they're formulated by quantum mechanics. But say quantum mechanics tells you there's a Hamiltonian associated with a particular system. Okay, but for one system, say for an atom or fermion or whatever, what Hamiltonian will it be? Okay, and the other very necessary details. So in classical physics, you have mechanics. Most important, two most important things: mechanics and electrodynamics. Okay, in here you have quantum mechanics. That's
Equations of motion.
in a way, yeah, the equivalence of classical mechanics in the quantum world. And quantum field theory, it actually consists of quantum chromodynamics and quantum electrodynamics. It's sort of an equivalence of the electrodynamics that we study in electromagnetism in the classical world. So quantum mechanics is the groundwork, quantum field theory is the build-up, and they constitute in quantum mechanics. One very important. In my job, I have mostly used analogies. Analogies are fun because to understand the abstract world, you need some visual idea. But again, remember, I have stated this multiple times. It is impossible to visualize or imagine the quantum world because our intuitions, our imaginations are based on classical world. They're based on the classical ways of thinking. So it's impossible to visualize the quantum world. So every analogy will have shortcomings and limitations. That's something very important. What's the way out? Learn maths. That's the only way out. You have to learn the maths behind all the necessary things in quantum, all the things in quantum mechanics, the rigorous maths. You have to understand it rigorously. And but how will it help me? Because see, I can visualize it in terms of the inelastic string, in terms of cat, in terms of chameleon, in terms of whatever I want. But there's also a visualization process based on mathematics. As a mathematical visualization, I can also visualize in terms of matrices. Okay, that's also a sort of visualization. So you have, if you want to grasp on the mathematical way of visualization, and that visualization, that analogy will have at least or not any shortcoming or any limitation. So you have to get the mathematical way of visualization. For that, you need to learn mathematics, you need to assimilate it, you need to understand it very properly, and then you can learn quantum mechanics rigorously, and you can learn, you can understand whatever I have said in the whole talk. Every point I mentioned, you can understand the mathematics behind each and every of this. And I can assure you that's way more fun than this. Way more fun. Because then you can make your own analogies and you can understand the limitations of those analogies. So yeah, learn maths, and finally food for thought. This is Sajadya. Okay. Swali right? Yeah, okay. So Schrodinger's plates. You have seen this meme a lot, I guess. And it's a fun one for physics enthusiasts. It's a pretty fun meme. Try to get some more fun. Whatever I have told you today, it's possible to try to find out why this scenario not at all resembles to Schrodinger's cat. And try to jot down like the points qualitatively. This was the Schrodinger's cat, this is it, yeah, and all this stuff. Try to find it qualitatively. How much it resembles with Schrodinger's cat, or if it's not at all, what are the points where it is wrong? And then you can find out whether this name is partially correct. Okay, fine, there you go, it's partially correct. Or partially wrong, still fine, let it go. Or fully wrong. Okay. So that's one food for thought. And my sole goal in this talk was to motivate you to learn quantum mechanics on your own. You can ask for help from any of us, me, Raja, Indra, Swali, and many more people here. So those who are studying quantum mechanics, none of us have still understood properly quantum mechanics, whatever we have read properly. They haven't. Now it's not possible. It takes a lot of time. So you can ask anyone, you can ask other seniors, you can ask for help. But this was my sole goal, to give you a visual idea how beautiful the quantum world is, and to how we can use mathematics to actually see not a proper metal microscope or plastic microscope, but a mathematical microscope to peek into an unobservable world, an unimaginable world. That was my sole goal to motivate you. That's it. To study it on your own. Go do the maths, learn linear algebra, learn whatever else calculus topics. I hope you know that, and then learn the maths of quantum mechanics. Learn quantum mechanics. I don't know if I'm successful in that goal, but if even one or two or whatever, a few people among you go and do it, my job is kind of done. I'm happy. Thank you.
As you know, this is an interactive session.
Yeah.
So if you have any doubts, please feel free to ask on the web. Any doubts? There are no dumb questions here.
You can ask anyone. Can I use a dog instead of a cat? Well, dog isn't that cute as a cat. Anybody else? Any non-adult type question? Anybody? Any question? No? Oh, everybody understood that? I'm good. Okay. Okay. Yeah.
Get is a notation used for vector in a complex systems. And one more thing that is the brand.
Yeah. It's a see. In the real vector space, say you have a 2D real vector space, okay? You can write the basis vectors, the orthogonal basis vectors as 0, 1, 0. I can take it. You can also write this in terms of column matrices, 0, 1, 1, 0, right? And if you don't think, see, you change it to a row matrix, 0, 1, row. So you have 0, 1, and 1, 0, right? In the 2D real space, but you change it to say this. Okay, so these are just the row version of this vectors. Okay, and you can. If you again follow those 8 rules, you can put these vectors there. You can see they also comply to those rules. So even these row vectors can form a vector space. Okay, and these vector space is called the dual space of this real two-dimensional real vector space. It's a dual space. So the ket is a vector in a 2D complex vector space, and the bra is a dual. What should I call it? Yeah, the dual of that vector in the dual space. Okay. So that helps. That actually also works as an operator. Okay. So it's fun. You have to read it how it works as an operator. And if you take the output bra of those bra, it will work as an operator. So yeah. Any more questions? Anybody? Okay. Thank you.
That concludes the GMTC, our first GMT series. Do mind the fact that any one of you can come here and talk about literally anything that you want, any topic that you find interesting, anything. It's fine. These series, the GMT series, the full form of it is a geographic talk. it's for everyone of you. Okay, there's no limitation on which class you have to be, or the knowledge you have. You can just talk about anything. We have set the arbitrary limit till MS21 just to make it less complicated so that everyone can give a talk. But yeah, in case anyone is interested, just contact one of us, mail us, text us on WhatsApp, anything. Anyone can come and